Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 11.9, representations of functions as power series. Now, we've already talked about power series in section 11.8, however, what we're going to talk about now is particularly one of the examples we dealt with. That example being where we just had some constant value for some coefficient c instead of a changing one. And we saw that if we evaluated that, that's essentially the same thing as a geometric series, and therefore has the evaluation or has the overall function display as c over 1 minus x. That means we can define specifically that this summation goes to that exact function. That's the kind of stuff that we're going to be talking about now, how to evaluate these with respect to geometric and geometric series and the ratio test. Now, in order to do a lot of these, what we're also going to need to do is make sure that we can get it into this specific form, something over 1 minus x, or some function of x. The most important thing about this is going to be that 1 minus bit. If we have 2 minus, we're going to need to make sure we divide everything so that it becomes a 1 minus. But our goal overall will be to try to make everything look like this c over 1 minus x. If we can do that, that means we can return from here back to this overall evaluation for a summation of a geometric series. Now, with that in mind, what we're going to also need is what we call term-by-term differentiation integration. Which means that if I were to take the derivative of this above series, say if I took the derivative of that summation, then that means I'd be taking the derivative of this polynomial. And because the polynomial just has pluses and minuses in between, I can simply take the derivative of each term individually, since they are not going to influence each other. Same thing is true if I were to take an integral. I could just take the integral of each term individually. And what that will really mean for us is that if we have a power series that looks like this, we can take the derivative of that power series and move that derivative on the inside of the summation. Same thing for an integral. We could take that integral and move it on the inside, which will allow us to take the derivative integration and the integral term by term, hence the name. Okay, now a lot of the times we'll have some series that look exactly like what we're trying to find. We just have to manipulate it a little bit to have the 1 minus bit. But sometimes we'll be taking derivatives or integrals of a beginning function and then trying to return back. So always try to keep in mind what you have to start with. And lastly, note that because we're evaluating these with respect to the geometric series, we have convergence for the geometric series so long as x is less than 1, or whatever this value to the n power is less than 1. So unlike the power series, which we were doing with the ratio test, where we had to also test x equals 1, the geometric series is divergent when x is equal to 1. Well, it's divergent when x is greater than or equal to 1. So we aren't going to need to necessarily check that. However, in realistic cases, there are going to be a few series that do converge at 1 or -1 or both or neither. So it's not necessarily going to be the case for us. We just won't check it ourselves because we don't necessarily have a lot of the theorems necessary to evaluate them properly. So let's do a couple examples of these. These first few examples should work pretty quickly. All we're going to try to do is try to manipulate it so it looks like that form of a geometric series. Remember, specifically, we want it to look like c over 1 minus x. And the most important part is that 1 minus part. If we can get that to show up, we should be able to rewrite this as a geometric series. So here I have 4 over 2x plus 3. So let's start with that. 4 over 2x plus 3. Currently, it doesn't look like 1 minus, but I should be able to rewrite it in that case. If I were to flip these around, make 4 over 3 plus 2x, so far it looks like constant followed by some values of x. And in order to make that a minus, I can easily do so by simply saying 3 minus a negative 2x. That's the same thing as plus. So far, so good. So I have the minus checked off. Now I need to make that first value a 1. Well, in order to do that, I'm going to divide everything by 3, or really, multiply the top and bottom by 1/3. If I do that, I get 4/3 on top over 3 times 1/3 is 1 minus negative 2/3 x. Now this looks like the form I'm looking for, specifically that 1 minus part. Everything else is going to be my c and basically r term. So this 4/3 here, that's going to be your c. This is going to be equivalent to your r term, or your radius. Your ratio, rather. So therefore, we should be able to take our original value, 4 over 2x plus 3. We should be able to write this now as a summation. In this case, c is 4/3, so we'll say 4/3 multiplied by r taken to an n power. So we have negative 2/3 x taken to the power of n. Note that I say power of n, that's because we typically want to start these with 0, so n equals 0 up to infinity. However, if you'd like to start this at 1 instead, then you just have the exponent be n minus 1, which is maybe more familiar to you from geometric series from section 11.2 and 3. Alright, so that's the series itself. So far, so good. What we also want to do is we want to find the interval of convergence for that function. Okay, well, the interval of convergence, we know the interval of convergence is defined as this being less than 1. So we'll simply say the absolute value of negative 2/3 x less than 1. And so the negative doesn't really matter. It can be a positive because of the absolute value. But we can multiply that 3/2 over it technically and get the absolute value of x is less than 3/2. So therefore, we have our interval of convergence from negative 3/2 up to positive 3/2. So that would be the rest of my answer. Alright, so that's how we're going to be approaching these, trying to make it look like that 1 minus part on the denominator. And then if we can get that, then we should be able to write that as a summation. Let's go to example 2. We'll find a power series representation and the interval of convergence again for the function 3x squared over x to the 4th plus 16. Again, don't worry about the powers on this. It doesn't really matter. It's really 1 minus a ratio. So all that matters is if we see this as a fraction and we can get a 1 minus on the bottom. And we should be able to do that with some help. Alright, so 3x squared over, I'll already flip these and say 16 plus x to the 4th. Well, easiest thing is to introduce that negative, so 16 minus negative x to the 4th power. And then all that needs to be done is then multiply top and bottom by 1 over 16. Then we have on top 3 over 16x squared. That's going to be my value for a. On the bottom, 16 times 1 over 16 is 1 minus, in this case we have negative 1 over 16 x to the 4th power. So this isn't necessarily the prettiest thing. We can continue that on the same line. But we should now be able to write this as a summation from 0 to infinity. We have our value for a on top. And we have our ratio here. So we should be able to say our a value, 3 over 16x squared, multiplied by our ratio value of negative 1 over 16 x to the 4th to the n power. Now you could do some more manipulation with this if you so please. For example, this 3 is independent on n, so you could pull it out. Technically the same is true for that x, but you can combine it in. You could do some more manipulations if you so please, but this should be perfectly fine for evaluation of the series. However, we have one more thing to do, and that's to find the interval of convergence. Because, again, it's a geometric series, we know that it is convergent so long as the ratio negative 1 over 16, negative 1 over 16, x to the 4th power is less than 1. That's not too bad to do. Again, forget the negative because the absolute value will get rid of that. Multiply both sides by 16. We have the absolute value of x to the 4th is less than 16. And if we take the 4th root of each side, the absolute value means the inside is going to be positive, so we're perfectly fine to take a 4th root. We have that x is less than the 4th root of 16 is 2. So therefore, we have a ratio or an interval of convergence from negative 2 to 2. So we're all done. Alright, so far so good. The first two have been relatively simple. There's just more algebra manipulation there. And that's how a good amount of them will go. But let's look at some trickier ones. For example, example 3 here. Find the power series representation and interval convergence for the function 2x plus 2 over x squared plus 5x plus 6. Whew, okay, well that doesn't exactly look like what we want. It looks more complicated on the bottom. There's 3 terms. We're typically used to just 1. However, there's a really nice way of dealing with this. There's technically a couple, but this is probably the best way. We have 2x plus 2 over x squared plus 5x plus 6. Now that bottom shouldn't look too bad. X squared plus 5x plus 6. I should be able to factor that. Say 2x plus 2. Over the bottom, we have two things. We have x and x multiplied to get x squared. Two things multiplied to make 6 and add to 5. That'd be 3 and 2. And now what we want to do is we want to make this into separate fractions. So think about partial fractions from a few chapters ago. We can make this into a over x plus 3 and b over x plus 2. If we could do that, then we could define each of those as a series. Okay, well, a will say, if we cross multiply appropriately, we can have a times x plus 2 plus b times x plus 3 should equal the top of 2x plus 2. And then we can rearrange some stuff. We have a plus b times x plus the constants. We have 2a plus 3b equals 2x plus 2. So that gives us a plus b equals 2, and also 2a plus 3b equals 2. If we multiply the top by, say, 2 and subtract away, we can take 2a plus 3b equals 2 and subtract away the first equation multiplied by 2. So 2a plus 2b equals 4. That gives us 3b minus 2b is 1b equals 2 minus 4 is negative 2. And therefore, if b is negative 2, we have a minus 2 equals 2. So a is then 4. Alright, that gives us now our two equations of 4 over x plus 3 minus 2 over x plus 2. Or you could even say plus a negative 2. Both of these are pretty easy to manipulate. We can write this as 4 over 3 minus x, or 3 minus negative x, plus negative 2 over 2 minus negative x, and then divide by 2 and 4 and 3 appropriately. And we get 4/3 over 1 minus negative 1/3 x, plus this one we're going to divide by 2, so we get negative 1 actually, over 1 minus negative 1/2 x. And so we have two series. Let's keep that in black. This first one we have a, which is 4/3, times the ratio, which is negative 1/3 x, taken to an n power from 0 to infinity, plus the second one as a summation. We have a as negative 1 times the ratio negative 1/2 x taken to the n power from 0 to infinity. Now, if you want, you can continue and combine those into one, particularly because they have the exact same summation, so it's very, very easy to do so. You could just say the summation of n equals 0 to infinity of 4/3 negative 1/3 x to the n power. In this case, that'd be minus all of those, so minus negative 1/2 x to the n power. That'd be decent enough as a full summation. However, looking at the previous separated ones is going to be very helpful for finding the interval of convergence. For the first one, we have the interval of convergence being true when negative 1/3 x, absolute value, is less than 1. So make that positive, and we have the absolute value of x is less than 3. So this one converges when x is less than 3. However, the second one converges. In this case, we have negative 1/2 x is less than 1. So that becomes absolute value of x is less than 2. So the second one only converges when x is less than 2. Therefore, for example, say if x was, say, 2.5 or something, then the first half would converge, but the second half would diverge, which means the whole thing would diverge. So therefore, we need to narrow down the interval of convergence to be this, to be just x is less than 2. When absolute value of x is less than 2, that also means the first one is convergent. But if x was 2 or more, then that means the second one would be divergent. So we need the whole thing to be convergent. Therefore, we have a convergence set of negative 2 up to 2. That'd be our interval of convergence. Okay, a little bit harder to do if you tried to work with this summation. So yeah. All right, now all of those have been relatively straightforward because they've just been some algebraic manipulation for the most part to get into the form of something over 1 minus something else. The next two are going to involve the term-by-term integration differentiation. Here we have find the power series representation and interval convergence for the function f of x equals natural log of 1 plus x. Okay, well, right now that doesn't look like 1 or a over 1 minus r. Not yet anyway, but I know that if I take the derivative of natural log, that 1 plus x will show up on the bottom, which should be one step closer. So if I take the derivative of that function, I get 1 over 1 plus x. I'm going to need to keep in mind that I took the derivative because I'm going to need to take the integral to get back. That's relatively easy though, particularly compared to the previous ones. We have 1 over 1 minus a negative x, and we're done. That's all we really need to make this into a summation. This is now the summation from n equals 0 to infinity of a, which is 1, times r, negative x, to the n power. Now, in order to get to f, to the original function, what I'm going to need to do is take the integral of that derivative I just took. So I'm going to then need to take the integral of that summation of negative x to the n power. However, what's nice about this, again, by the term by term, is that we can move the integral on the inside and make this the summation of the integral of all these terms, negative x to the n power of dx. What this then looks like is that I'm taking the integral. If I say we're to write this out, if n equals 0, I get 1. If n equals 1, I get negative x. If n equals 2, I get plus x squared, minus x cubed, plus x to the fourth, minus etc. dx. And I should be able to take that term by term, which I should be able to pretty nicely. The first one is going to turn into one integral is going to be x Second one is going to turn into minus 1/2 x squared. Third one will turn into plus 1/3 x cubed. And the next one, minus 1/4 x to the 4th power, plus 1/5 x to the 5th power, etc., etc. And we already see a pattern here. We see that this is becoming a summation, starting off with x, just one of those, and then x squared, and then x cubed. So we're really starting at n equals 1 would be nice. And we could say we're starting off with x to the n power. That seems to be true for the powers. The denominator always seems to be n as well, 1, 2, 3, 4, 5. So we're dividing by n. But we also have one more thing. We have this positive and negative happening. So we'll have -1, and we'll have to determine how we're going to take that to a power. Well, the first one is going to be even, the second one, or the first one is going to be positive, the second one is negative. Well, if I make this the power of n, -1 to the 1 power is -1, would make the first term negative. That's not good. So what we want, actually, is -1 either -1 or +1. We'll say -1. You could do either. But that would be a good representation of that series. Therefore, we have that the natural log of 1 plus x, which is our function, is equal to that summation. Again, benefit to this is that if natural log shows up in some weird integral or some differentiation, maybe some partial derivative, I can very easily now replace that with its summation here. Again, so long as, in this case, x is less than 1, it's convergent. So it converges to this series. And I should be able to replace it with this nice polynomial. Polynomials always being easier to work with. Let's do one more. Example 5. Find a power series representation and the interval of convergence for the function f of x equals tangent inverse of x, or arctan of x. So if you also know this is arctan of x, that works too. Okay, well, arctan of x, we're pretty familiar with that. We've seen that show up a decent amount of times in integrals up to this point. We know that if you take the integral of 1 over 1 plus x squared, you get the arctan of x. So therefore, we also know that the derivative, so if we have the function is tan inverse x, we know the derivative of that is 1 over 1 plus x squared. Or 1 over 1 minus negative x squared. Or, as a summation, from n equals 0 to infinity, we have 1 as a, and then my r, my ratio, is negative x squared to the n power. All right. Now, again, we took the derivative. So that means we're going to need to go back. We need to go back to tan inverse by taking the integral of all those. So let's write those as terms. So say if we have n equals 0, then we just have 1. If n equals 1, we have negative x squared. If n equals 2, we have positive x to the 4th power. And then minus x to the 6th power. They will multiply the exponents. Then you start to see a pattern here. Plus x to the 8th, minus x to the 10th, etc., etc. And if that's the derivative, we should be able to find the function of x by taking the integral of all of those terms. If we do so, what we get is x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th plus 1/9 x to the 9th minus 1/11 x to the 11th, etc., etc. And we already see a pattern here, kind of like before. In this case, it's not every single value of n is going to be represented, but we see x to the 1, 3, 5, 7, 9, 11. These are all odd powers. So we should be able to write our function, tan inverse of x, as the summation. Again, we'll start, we can start at 1, 2, however you would like to start. In this case, I'll keep at n equals 0, which is very typical. The last one we started at n equals 1 for not exactly a reason. You could do 0 and then just add 1 to each of those ends. But we'll start at 0 here because that's kind of how I derived this anyway. And we see that we can define these odd numbers by simply saying, all right, well, x taken to 2n plus 1. Odd numbers you can always do as 2n plus 1 or 2n minus 1. It really depends on where you start. If you start at 1, then you'd have 2n minus 1. If you start at 0, you have 2n plus 1. Likewise, the denominator is also going to be represented by those odd numbers, so we also are going to divide by 2n plus 1. And yet again, we also see an alternating component to this, a negative 1. If we take negative 1 to the n power, just n, then we see negative 1 to the 0 power is 1, and that would correspond to the first term. Negative 1 to the 1 power is negative 1, which would correspond to the second. So this seems to be good. Therefore, we have our summation. And for this last one, we also notice that the only things taken to the power of n are that negative 1 to the n and x to the 2n plus 1. So that also is going to mean that the interval convergence, just like the last one, is also still going to be just x is less than 1. Just taking powers of either side, no matter how complicated, it's still going to leave 1 on the other side. Alright, but that's it for how to do some basic representation of some power series using geometric. If you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. With that said, I hope you have a nice day.